In this video, we're going to take a look at section 2.2 on histograms. A histogram is essentially a bar graph of a frequency distribution. So we looked at the topic of frequency distributions in section 2.1. So if you haven't watched that video yet, you should probably watch that one first before proceeding any further with this video. Each bar represents a class, and the height of each bar indicates the frequency of that class. All right, so it's basically taking a frequency distribution, which is a table, and converting it into a bar graph. And there's some rules about how that's supposed to be done. So here are the rules for constructing a histogram. One of the most common mistakes I'll see students make on a test when they're drawing their bar graph is they will have gaps in between the bars. Histograms do not have gaps between the bars. Some bar graphs, that's okay to have gaps, but not for a histogram. So each bar, each consecutive set of bars should be abutted against one another. I'm trying to think, is there a better word for that? But they should be flush with one another. There shouldn't be any gaps. The classes are labeled on the horizontal axis using either the class boundaries or the class midpoints. So we talked about how to find the class boundaries and midpoints in section 2.1, and it might have seemed like a useless exercise in that section, but here we are using that skill, if you will, in section 2.2. So being able to find class boundary, class midpoint is going to be useful in section 2.3. We're going to make some use out of it. The frequencies are indicated on the vertical axis and must start at 0. So you might be tempted in a certain data set, depending on what the frequency distribution looks like. Let's say the smallest one is 20 and it goes up to like 50 or something. Let's say those are our frequencies. You might be tempted to say, well, since the lowest one is 20, let's just start at 20. And then we'll go 20, 30, 40 from there. That is not acceptable. That produces a very misleading looking graph. So for a properly constructed histogram, it needs to start at 0. The graph has to be drawn from 0 up to whatever the different frequencies are. All right. And so let me, I'm sorry if you cannot read the words there. So let me scroll down a little bit so you can see that. So as I was saying, the vertical axis is the frequencies. It must start at 0. This will result in the height of each bar representing the frequency for each class. Right? So however high up the bar goes, that's the frequency for that particular class. All right. So I want to revisit the data set that we used in the video for section 2.1, which was this data set that you see here on the screen right now. These are the critic review scores for the game Animal Crossing. There's 107 of them. It might not be all 107 professional critics. I kind of said that funny, but this may not encapsulate all professional critics is what I wanted to say. So it's 107 of those professional critics. So we have this sample of data here. And in the video for section 2.1, we constructed this frequency distribution. And then I proceeded to make a complete mess of that screen because we dissected, and that's a word I was looking for when I recorded the video. Now I'm thinking of it. We dissected every part of a frequency distribution. We talked about the lower class limit, upper class limit, all that stuff. And so this is what that frequency distribution was for the data set that we just looked at. What we want to do with this frequency distribution is convert it into a histogram. And I'm going to try to draw this out by hand. It's not going to look the best. I remember one time using a website to construct a histogram, but it had some shortcomings as well. So I don't really have a good tool. I guess I could try to use Microsoft Excel, except that this is actually a new computer that I have, and I don't have the Microsoft Office suite yet. Keep running into issues because of that, so I probably will go ahead and make that purchase soon, but I don't have a way to construct the histogram on Excel. That'd be another way you might do that using technology. I'm just going to draw it by hand. On Math Excel, or not Math Excel, on My Stat Lab, when you are asked to construct a histogram, the problems are going to be multiple choice. So you might be tempted to not actually construct it yourself, because if you look at your multiple choice options, you can figure out which one matches the data pretty easily. I would highly recommend that you still go through the exercise of constructing that histogram by hand, because that is what you will be asked to do on the test. So on the exam that you have in my class anyways, if you're taking my class, it will not be multiple choice. You will be given a problem that will say, here's a set of data, or here's a frequency distribution, construct a histogram from it. And you will need to know how to draw that out by hand, and you won't have multiple choice options to help you. All right, so the first thing I'm going to start with is drawing a X and Y axis. Now, the critic scores are all positive. In fact, they start at 70. That's the lowest one, if you recall, from section 2.1. And they go up to 100. And the frequencies can't be negative, right? You can't have a negative number of data values in a particular class. So that has to start at 0, but it doesn't have to go negative, right? And so we really don't need this. We don't need, I'm doing a horrible job already. We don't need all 4 quadrants of the Cartesian coordinate system to graph this histogram, because we don't have negative frequencies and we don't have negative values in our classes. So I'm really just going to be using this part of a Cartesian coordinate system to draw this this histogram. All right, and so we will have a y-axis here, which will be the frequencies. And then we'll have the x-axis here. And this will be the review scores. All right. And this one's going to be kind of tough because we have such a range of frequencies. We have as low as 1, and we have as high as 59. So I got to make sure. Now we have to start at 0 either way, but we're going to have to go all the way up to 59 on the y-axis, right? That's my largest frequency. I need to make sure that number is going to fit on my graph. And so I'm considering the scale that I want to use here. I'm going to start at 0 because that's the rule. We have to start at 0. But I don't want to go by ones, because then I'm going to have to go 1, 2, 3 all the way up to 59. And that's going to be really hard to mark. So I think if I go by tens and I keep it fairly small, I can probably get to 60 pretty easily that way. So let's have this be 10 and this be 20. Now, for this graph to look proper, this scale that I'm using has to be consistent. I can't go 10, 20, 50, 60. I can't skip like that. So it has to be, if I'm going to go by tens, it has to be tens all the way through. And the distance between each mark should stay the same. So I'm doing my best by hand to make sure that this gap here from 0 to 10 measures the same distance as this gap from 10 to 20. And I'll try to do the same thing here. So from 20 to 30, 30 to 40, 40 to 50, and then 50 to 60. So I tried my best to keep this spacing the same throughout. It's not perfect. I got a little bit cramped up here, but I think it'll be adequate for our purposes. Now, the frequencies have to start at 0 for the histogram to be drawn properly. The classes, however, do not. I don't have to go 0, 10, 20, 30, because I'm not going to even have any bars here until I hit 61 to 70, right? And so I'll just have this big empty space before the bars start showing up, which again, there may be some reason why you'd want to illustrate that there's, for instance, if you're a developer of this game and you want to illustrate how well received it was, you might want to illustrate that we didn't have any negative reviews. Our lowest review was a 70. It didn't start till up here. So maybe you'd want to keep that gap there to emphasize that point that the reviews are on the upper end. But we don't have that particular agenda. So we're just going to jump right to where the data starts on the x-axis. So you don't have to start at 0 here. So I think I'm just going to start this at, 60, let's say, right? So we'll just kind of start at 60 here. Now for the bars, when we draw them, they should also be the same width throughout because our class width is the same throughout the entire frequency distribution. But the numbers I want to mark here, this is kind of why I'm pausing, I want to use the class midpoints or the class boundaries. And so I don't want to put like what some students will do is they'll say, okay, here's my first bar, and it's going to be really small because it's just 1, right? And I'm doing a bad job drawing it. And some students will label this as, oh, this is 61 through 70. I'm doing a bad job all around. This is 61 through 70. That is incorrect. So if that's what you do on the exam, you're going to lose a point or 2 because you don't want to label the bars using the class range, if you will, from 61 to 70. You either use the class midpoints or the class boundaries. You don't need to do both. You pick one or the other. I personally think it's easier to use the class midpoints. So if you go back to our video from section 2.1, we calculated the class midpoints here as this one being 65.5. Then we used the class width to generate the rest of the midpoints. So the class width is 10. So the next midpoint will be 10 away. It'll be 75.5. And then 85.5. And then 95.5. So we can use this to label each bar. We'll use the class midpoints. If you're using the midpoints, that label should go right in the middle of the bar that you draw. So going back to our first bar here, I'm going to erase this arrow. I'm going to erase this whole thing because, again, that's just not the right thing to do. And I'm going to erase the 60. So we're starting at about 60. But what I'm going to end up labeling here is the midpoint, and it'll be right in the middle of the bar. This is going to be 65.5, and that represents the first class. It had a frequency of 1. This might be a little bit too high even for that, but I don't think I could draw it any narrower on here. So it's just really low. The next bar, remember, we don't want a gap. So if you do this on the test, you're going to lose a point because there should be no gaps here. Your next bar should start right where the first bar ended. Right, so let's undo those marks. I don't know if I want to stick with the same color. Maybe I'll go ahead and use red here. So my next bar is going to start right here. And the height of it is 11, right? The frequency for the next class was 11. So I just want to go just a shade past 10. I might have went a little too far, but again, it doesn't have to be perfect. And as well as I'm drawing, another reason I like to do this by hand is because I want to show you what I'm okay with on the test, because I'm not going to expect you to draw your histogram any better than I could do it myself, right? So this will be okay. It doesn't have to be perfectly at 11. Just somewhere in that neighborhood would be acceptable. Try to make that a horizontal line, not too wavy like I did. And the width of the bar should be about the same. We want, again, technically should be exactly the same, but when you're drawing it by hand, show me that you made the effort to make the bars look about the same width. So if you do something like this for your second bar, you're going to lose a point for that because this bar is way wider than this one, and it doesn't look like you really cared about it. So try to get it in the neighborhood of the same width. So maybe something like this that looks about the same width there. And again, we will label the middle of this bar with the class midpoint, which is 75.5. All right. And so that's going to be the second bar. Our third bar is going to be the highest one, and this is going to be hard for me to draw. I know I'm going to mess this up, but it needs to go all the way up to 59. So again, starting right next to the bar that we just drew, the third bar should extend all the way up to almost 60. Right? So I should be just a little bit under 60 there. I want the gap of the bar to be, or not the gap, I'm using the wrong word there, the width of the bar to be about the same as the width of these two. So I think that just about does it. I feel like my bar widths are a little wider for some reason. I don't know. Maybe it's just easier for me to draw that way, but these look a little cartoonish to me. I feel like they should be narrow, like it's more professional if they're more narrow for some reason. So it's just kind of bothering me a little bit, but Again, this is fine. This is fine. And again, label the midpoint. So make sure you're labeling the midpoint for each class for every bar. And so this should be 85.5. And then the last bar has a frequency of 36. So that's going to be about halfway. This is probably a better idea. Kind of mark that first. And so our last bar, again, will be right up against that third bar. It'll have a height of 36. Oh, and we want the width of the bar to be the same as the first three. So about right there. And then here we have, I guess another reason for drawing them so wide is so I have room to write these midpoints in there. And there's our third bar, right? And that is a perfectly fine drawing of a histogram. It has no gaps between it. We label the x-axis with the class midpoints or the class boundaries if that's what you prefer to do. What was the third thing that I mentioned on here? I can't remember. And the frequencies start at 0, right? And I should have mentioned that the width of the bar should stay the same. There's a lot of little details that I didn't really type out completely. So, but I mentioned them verbally. So hopefully that's good enough. So this is our histogram. Alternatively, if you didn't want to use the class midpoints, you could use the class boundaries. So if you remember, and so these are the midpoints here that we got from section 2.1. The boundaries would look like this. So we have between 70 and 71, that's going to be 70.5. And then again, the spacing there is 10. So I get the next one by adding 10, 80.5, 90.5. And those are the boundaries between the classes. But remember, there's a boundary at the end of the frequency distribution, and rolling it back, there's one just before the frequency distribution begins. And so you could use these as your labels. If that's the route you want to go, then those labels should go at the edges of the bar, not in the middle, but at the edge, at the boundaries, right? And so this would be 60.5 here, because that's the boundary at the beginning. This would be 70.5. This would be 80.5. This would be 90.5. And then this final boundary here would be 100.5. And you could do that instead. You don't need to do both. You know, I don't have to do the boundaries and the midpoints. Just one or the other is fine. I just wanted to show you both of them in this example. All right. So hopefully that gives you a good idea of how to construct a histogram from a frequency distribution. Let's take a look at some examples from your homework. So here, we don't have to construct the histogram. It's given to us. So again, notice no gaps. This is what a professional one should look like. These are pretty wide too, I guess. But there's no gaps between the bars. The frequencies start at 0. I keep feeling like there's 3 things I want to mention, and I can only ever remember 2 of them. And they're labeling the horizontal axis. This they might not be doing perfectly. These may not, in fact, be the actual boundaries. So they kind of break their own rule there a little bit with the tool they're using to construct these histograms. So these might be, you know, based on the boundary, but then rounded to the nearest whole number. So maybe the boundary is really 119.5, but they just round it to 120 for convenience sake. And so here we're being told the histogram to the right represents weights of members of a certain high school debate team. All right, and these are in pounds, surprisingly. So, you know, usually in scientific studies you use kilograms, but they're using pounds in this particular case. And so, you know, just to make sure you can interpret the data that's being presented in this histogram, the height of the bar is the frequency. So for this first class, this first bar, the frequency is 3, which tells me that there's 3 data values in this class, which contains values between 100 and 120. Again, I wouldn't worry too much about the technicalities of what's the class boundary and whatnot. But the way I'd interpret this first bar is that there were 3 students that weighed between 100 and 120 pounds, right? That's the data that you see here in this graph. There was 1 student, right? Because the height of this bar is 1, that weighed between 120 and 140. There were 4 students that weighed between 140 and 160. So you get the idea. What we're being asked for here is the class width, right? So again, this may not be exactly the class boundary, but it should still respect that distance. So in going from 100 to 120, the distance there is 20, right? So I'm going to take this value and subtract them to get my class width. And I find that the class width is 20. And you should get the same answer no matter where you do that calculation. So if I did the calculation, let's say here, right? You just take two consecutive class boundaries, 200 minus 180, and you get the class width. And you should get the same answer no matter which two class boundaries you use, as long as they are consecutive, one after the other. All right. So in the video for section 2.1, I mentioned to find the class width, you take two consecutive lower class limits or two consecutive upper class limits. But you could also take two consecutive boundaries if that's the information you have, or two consecutive class midpoints. Those should also give you the same value for the class width. All right, so that's the class width for this particular set of data for this frequency distribution. What are the approximate? So again, notice they're admitting here that there's some ambiguity with what the lower class limits are, what the upper class limits are, what the class boundaries are in the graph that's given, because they've rounded it, they simplified it to make the graph a little more readable, a little bit easier to look at. So they want us to approximate what the lower and upper class limits are for the first class. So thankfully, they're not going to make us do it for all of the classes. And so the first class here is this first bar. Even though they're using 100 as the class boundary, I would say that's probably more likely the lower class limit for that class. You wouldn't want 100 to be your actual boundary, because 100 is going to be a possible data value, and you wouldn't want it to fall in that gap, because remember, the class boundary is in the gap where data values cannot occur. And 100 seems like a reasonable, likely data value that you could get from weights. So I'm guessing more than likely this boundary is 99.5, and that 100 is really the lower class limit for that first class. So we're going to say the lower class limit for that first class is 100. The upper class limit for that first class is the 120, even though they're using it as the boundaries in this graph. Okay. It doesn't ask this, but I thought let's make sure we understand how to interpret these histograms. So I had one more question that I could think of off the top of my head right now that would be worth exploring, which is, what's the total number of students on this high school debate team? Right. So we mentioned there were 3 students that weighed between 100 and 120, 1 student between 120 and 140. And again, some of the ambiguity here is, what if you had a student that weighed exactly 120? Are they being counted in the first class? Are they being counted in the second class? So again, the labels they're using on this axis probably aren't exactly the class boundaries like they should be. The frequency in this class is 4. So 4 students that weighed between 140 and 160, 5 students that weigh between 160 and 180, 3 here, 1 here, and 4 here. So what's the total number of students on the debate team altogether? You would add up all these frequencies to get the total number of data values, which would represent the total number of students on the debate team. All right, so we have, this would be altogether here 8. This is also 8, and this is 5, right? So if you add those up, you just kind of chunk it, group numbers together and add up that group. And then once you've added up all the groups, add the results from all the groups together, right? That's one way of approaching it. Or you could use a calculator and do 3 plus 1 plus 4 plus 5 if you wanted to do it that way. Either way, you get that the total number of students on the debate team is 21. And remember, I mentioned this at the end of the video for section 2.1. Hopefully you watched it to the end. I know it was a long video, longer than it should have been. But at the end, I mentioned N is the most common letter that is used to represent the total number of data values. So whenever you see N getting used, that's how you should interpret it. It's representing the total number of data values in the data set. All right. So why don't you give this problem a try, pause the video, and see if you can construct the appropriate histogram given this frequency distribution. This is a problem that you will see on your homework assignment if you're in my class. So this will prepare you for that. You'll see one just like it in the homework, and you'll see a couple of other ones similar. It'll be different data, but where you're given the frequency distribution and you're asked to construct a histogram. I conveniently left off the multiple choice. As I mentioned earlier, these problems on your homework will be multiple choice. But on the test, it's going to look like this. You're given the frequency distribution. You draw the histogram. You don't get multiple choice options. You have to draw it yourself by hand. So it'd be a good chance for you to practice doing that. So pause the video. See if you can put that histogram together. I'm going to pause my recording so you don't have to watch me go through the construction again, because we already did that with the Animal Crossing data. And then resume the video, and when you do, you'll see the answer on the screen. You can compare your answer to my answer, and I'll maybe explain how I came up with my answer briefly. All right, so pause the video and then resume here in just a minute. Okay, so don't panic. I know the screen was blank just a second ago, and now it's this big giant mess. And, I did the best I could to draw that histogram. It looks a little funky, but not the worst I've ever drawn, I'm sure. And while you were probably expecting to see the bar graph over there, you maybe didn't expect all this other work on the screen. And I didn't really mention it when I was kind of sending you on your own way to do the problem yourself. But hopefully, if you did follow my instructions and you pause the video and you're like, okay, I'm going to draw this histogram on my own first, you should have realized that something you were going to have to do is to calculate the class midpoints or the class boundaries, whichever one you want to use. Again, you don't have to do both. My preference is to use the midpoints, and so that's what I've done here. Right? So I calculated the midpoints for each class, and the best way to do that is you calculate the first one. That's what I've done down here, right? 6.0245 is what I got as my first class midpoint, and I found that using the formula that we talked about in section 2.1. You add the upper class limit and the lower class limit for that class, and then divide by 2. And that's averaging those two numbers together, and that tells you the number exactly halfway in between. And it's not a pretty number, right? These numbers are fairly precise, right? They have several decimal places, and so these numbers are kind of hard to work with, which I almost was tempted to pick a different example for my video, because I was like, oh, I don't really want to deal with those numbers. It's 3 decimal places, right? But our class midpoint is 4 decimal places, right? But it's on the homework, and I thought, well, if I'm going to make you guys do it on the homework, I should be willing to do it as part of my lesson, right? And so the other ones on the homework seemed a little more friendly in terms of the types of numbers. Now, if you look at the data that we're actually looking at, which I didn't bother to read before, we're looking at the weights in grams of quarters before 1964. And so there's not going to be a lot of variation in those weights, right? There's a little bit, right? They can be as low as 6 grams, as high as 6.399 grams. But when they make those quarters and they mass produce them, they're done in such a way that they should be fairly consistent. And we're seeing that in the data, right? The coins all weigh roughly about the same, but there's a little bit of variation between them. But you only find that variation if you go to 3 decimal places, right? If we rounded this to the nearest whole number, these would all equal 6, right? So in order to get that variation, you have to measure them pretty precisely. And so that's why we're dealing with data that has a lot of decimal places in this case, right? And so we get this horrible class midpoint of 6.0245. And then to get the rest of the class midpoints, the quickest way to do that is to use the class width. And so I calculated the class width here. You find that by taking either 2 consecutive upper class limits or 2 consecutive lower class limits. And you want to look for the easiest calculation to do. And to me, it looked like it was this one. I took this lower class limit and the next one. Right? These are 2 consecutive lower class limits, and I subtracted them, and you get a fairly nice class width, relatively speaking to the data we're dealing with, of 0.050. And so to get the next class midpoint, you take the first one, you add 0.050, so I'm adding here. Okay, I hate when I do that. I'm sorry, I moved the screen that I'm using to record, which it doesn't let me do otherwise, but it sure lets me do it when I don't want to. Let's see, can I move it back? Okay, there we go. Okay, so I'm adding 0.050 to, see if I can erase that stray mark without moving the screen, that first class midpoint, and that's how I got the next one, which again is not the greatest kind of number you want to be dealing with, but you get 6.0745. Then you add 0.050 again, and you get 6.1245. And you start to notice a pattern, right? The 245 is the same again, except now we're at 1. And then when you add 0.050 again, you get 745 again, except again, the first decimal place is 1. When you add it again, you get the 245 again, then you're back to the 745. So it's just going to alternate between those last three numbers. And the only thing that changes is the first decimal place keeps creeping up, right? So we have 1s, then we have 2s, then we have 3s. So it's not as bad as it might look. If you're using a calculator, there's a really easy way to do this, which is you add 0.050 the first time to get 6.0745. Then just hit enter again. You don't have to type in the addition again. If you just hit enter again, it assumes you want to repeat the last operation. I'm pretty sure that's how most calculators work. And it'll give you the next one. You hit enter again, it'll give you the next one. And so you can just kind of zip through them that way on a calculator. So then I drew my axes here. We have to start at 0 on the y-axis. That's always required. But for the x-axis, I kind of jump to where the data begins. And so what I did is I didn't draw the bars first. I labeled my axis first. And so these are the values in grams of the quarters. And I labeled the first class midpoint, 6.0245 here. And then I went a certain distance away, put another mark, and tried to keep, I failed, but I tried. And that's what's important on the test when you're drawing this on your test. I want to know that you try to keep the gaps the same. So when I marked the next class midpoint, I tried to keep that gap the same as the first gap. And same thing here and same thing here. Now I kind of failed here at the end because like these kind of get a little more squished together. And so you can kind of see this bar is a little skinnier than this bar is. But like I said, it doesn't have to be perfect when you're drawing it on the test, right? Just make an effort and it should come through when I'm looking at your work that you made that effort. All right. And so I made 8 marks for the 8 different classes that we have here. So another thing you might have realized is there's a lot of classes in this set of data. For every class, you're going to have to draw a bar. 8 classes means I'm going to have 8 bars in my histogram. And so I made those marks and then I went back and labeled them with the class midpoints, right? So I labeled each one. Now these numbers, there's so many decimal places, they would run together really easily. So one way you can kind of avoid them bleeding into one another is to write them at different levels, right? So I have these numbers here written sort of at the normal level where you would normally want to write the numbers on the axis. Then I used an arrow to write some of them a little bit further below, so I'd have space to actually write out the number. And then I went back and wrote this third one in a little bit above and kind of just tried to squeeze it in there. So it's not perfect, but I did manage to write all the numbers in there some way or another. And then I went back and drew the bars, no gaps between the bars, and I made the heights equal to the frequency. And notice that on my axis, I didn't go by tens like I did in my first example because that is not warranted by the data that we have, right? This data stays fairly small. The highest frequency is 12, and I thought I can reach 12 pretty easily if I just go by ones. I don't need to go by 2s or by 10s or anything like that. So each mark here counts as 1. Now for my labeling, I only labeled every other one because again, they would start to bleed together. And again, I kind of messed up on the spacing here, right? Well, no, there's 2 here. This is 3 actually. So maybe I didn't do such a bad job, but you want to try to keep these evenly spaced out as well when you're drawing it by hand. Right. And so here's 2. So I drew my first bar with a height of 2, second bar with a height of 4, third bar with a height of 7, which is this mark right here. So not quite as high as 8, hopefully. So I'm down here around 7. The next bar at 10, I might have missed the mark on that one. Maybe that should have been a little bit higher. The last bar, not the last bar, but the highest bar at 12, right? So that's supposed to match up to 12. And then this is 4. This is 5, a little bit higher than 4. And then the last one was 1, right? And I tried to have all the bars with the same width, no gaps between them. And so this is not a terrible drawing of a histogram when you're doing it by hand. It doesn't look as nice as it would if we use some kind of technology like Microsoft Excel, but it's good enough for what I would like to see on the exam. So if this is what you gave me as your answer on an exam for this problem, it's 100% on that particular problem. All right. Okay. So hopefully you've had some practice. You got to see how to construct a histogram. Hopefully you got to practice it a little bit with this problem. You'll have a little bit more practice with it on the homework, except on the homework it's multiple choice. So again, don't fall into that temptation of just using that to your advantage, because you won't have that advantage on the test. At least do a couple of them by hand just to make sure you have the right idea on how to make them look. There's a couple of more topics I want to address in this section before we end the video. I talked about this actually in section 2.1 without officially defining it. So maybe in the textbook they don't really talk about it until now. But I mentioned the idea of skewness in section 2.1. So a distribution of data, so I'm going to officially define that now. A distribution of data is skewed if it is not symmetric. So remember, symmetric means it looks the same. If you start at the middle, it looks the same to the left as it does to the right. That's what symmetric looks like. Skewed is not symmetric. It will not look the same to the left as it does to the right if you start at the middle. And it's skewed if the data extends more to one side than the other. And we can see that happening with the Animal Crossing data. So if we go back to this histogram, we see here's the middle right here. It's 4 bars. It's kind of hard to really have a middle. In fact, I was just reading that a histogram, or not even histogram, a frequency distribution, you really want to have at least 5 classes. So I kind of broke a rule on how I constructed this. I should have divided it up a little bit better so we had at least 5 classes instead of just 4. But we can see that the data is skewed to the right here, right? And we can see that in the original set of numbers, right? That most of the data is in the 90s and 100s. And so it's not symmetric. There's not a peak in the middle and it looks the same to the left as it does to the right. The data is more clumped to the right. It's higher up. And so we would say that data is skewed to the right, which you could also say is positively skewed. And you might say, why positive? You'll learn more about that as we dig a little bit further into different statistical tools. We're going to talk about something called a z-score in chapter 3. So it's really just around the corner, but then, we don't really use it a whole bunch until later in the course. But for a z-score, typically the middle of your data, the z-score is 0. And then it's positive to the right and it's negative to the left. So when we say it's positively skewed, that positive reference is really to the z-score of those data values, which you're going to learn more about later. The data is skewed to the left if there's more data values on the lower end, and we would say that's negatively skewed because, again, that's where the z-scores would be negative. All right, and so this is something you might be asked about in the homework, is to look at a histogram. And what's nice about a histogram is you can get a good visual representation of the data to better see if it's clumped more to the right or if it's clumped more to the left, or if it's symmetric, if it's clumped in the middle and kind of low on the ends. And you can interpret the distribution of the data. So distribution just means how is that data distributed among the possible values. And there's different possibilities. We're actually going to take a look at some examples here on this screen here. Right. So a normal distribution is one where it's clumped in the middle and it's low on the ends and it's fairly symmetric. From the middle, it looks the same to the left as it does to the right. And that's exactly what you see this histogram doing. So notice it's not perfect, but in general, the pattern it exhibits is it's high in the middle, low on the ends, and it's relatively symmetric. And so this is a good example of what you would see if your data had what's called a normal distribution, which another name for that is a bell-shaped curve, right? So if you kind of outlined the pattern of the data here, you would get something like this, and this kind of gives it that bell shape. So this would be considered a normal distribution. So on the homework, if you're asked, does your histogram appear to have a normal distribution? You would say yes if it has this particular pattern. And you would say no otherwise. So going back to the examples that we've done, this one does not have a normal distribution. Now you might say, wait a minute, it's clumped in the middle. It looks symmetric as you go to the left or to the right. But what prevents it from being a normal distribution are the ends. It has to be low at the end, and it has to just get lower as it goes towards the ends to the left and to the right. And that doesn't happen with this set of data, right? We get a sort of a second peak to the left and a second peak to the right. And so this data is not a normal distribution. And there may be some other fancy name for it that I'm not aware of. I would just say this is not a normal distribution, and that's probably all you would have to say about it. You don't have to give it a different label. Our Animal Crossing data, again, if we had more classes, we'd be able to see this a little better, but also is not a normal distribution. It's skewed to the right. So we would say this data is skewed to the right, and also is not a normal distribution. All right, so it's kind of fun to say this is not normal, but what we mean by that is it does not have a normal distribution. The data doesn't peak in the middle and attenuate as it goes to the left and to the right from there. So it doesn't have that bell-shaped curve that we would want to see. This one is, I should mention about skewness, we would also say this is not skewed to the left or to the right either, because the data, it kind of is equal on both ends. It's not clumped just to the left or clumped just to the right. So again, it kind of has, if you outline the bars, it has sort of a distribution that looks like this, which again may have some name, but I'm not familiar with what that name might be. But this is not a normal distribution. A bell-shaped curve has to look like this. Skewed to the left would look like this. Maybe I could exaggerate that a little bit better. It looks something like that. And skewed to the right would look something like this, right? So this is what the general outline you would expect to see if it was skewed left, if it was normal, or if it's skewed right. This is what you would expect to see. All right, so maybe I should have drew that on a different screen other than this screen, but at least it's somewhere on the video. And so that's a good reference for you to, make draw a conclusion from the pattern that you're seeing in the histogram, right? Okay, so let's take a look at these other ones. This one would be skewed left. So that follows the outline I mentioned on that previous screen that we just were on, right? So again, it's clumped more to the left. It has a peak, but it's not really in the middle. It's more shifted to the left end of the graph, and the right end it drops off very rapidly, and it's very minimal, right? And so this would be skewed left. This is what skewed left looks like. And I'm sorry, this one may be hard to see. Let me adjust the screen. And this is a part of the picture I took, so I'm sorry that's there. We're just going to be stuck with that. But if we outline this, we would see that this follows this outline. This is skewed right, or positively skewed. And this other one that I conveniently skipped over actually does have a name. So this is none of those things. It's not normal. It's not skewed left because we don't have a clump just to the left. It's not skewed right because we don't have a clump just to the right. This is fairly evenly distributed. The data value is equally distributed among the range of possible values, right? We have about the same number here around 0 that we do around 1, that we do around 2. It's just kind of the same all the way through. The special name, so this one I happen to know, because we actually will see it later in the course, is called a uniform distribution. It's spread out uniformly among the possible data values. All right. So those are descriptions that we have for different types of distributions based on what the histogram looks like. All right. So let's take a look at this one. The last digit of the heights of 64 statistics students were obtained in an experiment. Specifically, do the heights appear to be reported or actually measured? All right. So this is another thing you might try to guess at. So I'm going to kind of cheat on this one. So as I mentioned, this is maybe a case of do as I say, not as I do. On the homework, you should try to construct these by hand rather than just use the multiple choice. But I left the multiple choice on this one for a reason, because I knew this would be the end of the video, and I just kind of wanted to pick the histogram quickly, which I think we can do fairly easily here. Now, we can rule out A, because if you look at the first class, and this one's kind of a weird frequency distribution because the classes don't have a width, really. I guess they do have a width, but they don't have any range to them. because we're just looking at single digits. Either the last digit is a 0, or it's a 1, or it's a 2. And so there's not a range of values. So I guess what's missing is there isn't a lower class limit and an upper class limit. There's just a value that represents the class. And the frequency for this first class is 16. So for 0, it's 16. And we see another peak here. So this is what jumps out at me, is that we have these peaks in the number of data values and the frequencies for 0 and for 5. And so that's what I'm looking for in my choices over here, is which graphs seem to exhibit that same peak. We should have a peak in frequency at 0 and another one at 5. So A immediately is ruled out. It's kind of the inverted version of that, right? We actually have troughs. We have valleys at those numbers. We should be seeing peaks. But B, C, and D, I kind of thought, oh, it's going to be obvious, but actually all three of these have those peaks as well. So we're going to have to dig a little bit closer. Now, another interesting feature of this frequency distribution is that 1, 2, and 3 are all the same, which means it should be uniform for those particular classes. And so D gets ruled out because that uniformity is missing here, right? 2 dips down and then 3 jumps back up. That shouldn't be happening. Our data here says it's 4, 4, 4 for all three of those. So it's either B or C. And what's a distinguishing feature between these two? Oh, that's kind of hard to tell. Oh, okay. The graphs actually are identical. If you look at the bars themselves, everything's the same. Like the relative heights of the bars are the same. The difference is in the scale they're using. This one goes up to 36. This one goes up to 18. 36 is a little too high for the frequencies that we're seeing over here, right? The highest one is 16. So this bar is close to 36. Which means this bar is like 32, 34, somewhere in there. The frequencies don't get that large. And so I can rule this one out as well. So C is the correct option. So that's the cheating way of getting the histograms correct on your homework, which again, I understand you're busy. You want to get the answers right as quickly as possible. And I wouldn't be upset if you did that on a couple of them, once you feel like you got the hang of how to put a histogram together by hand. If you want to do the rest of them by this elimination method, that'd be okay with me, but just make sure you are able to do those graphs by hand. So C is the correct answer. All right. Now, what can be concluded? I thought perhaps it might ask, is this a normal distribution? So I want to ask that question. Does this frequency distribution appear to have a normal distribution? Is it normally distributed? The answer is no. It doesn't have that bell-shaped curve, right? It doesn't look like this. And so this is not a normal distribution. Let's try that again. This does not appear to have a normal distribution. So this is not normal. I would also argue it's not skewed left or skewed right. It, again, has some kind of other type of distribution, which may or may not have a special name. There's 2 peaks. There's a peak at 0, a peak at 5, which is what's kind of unusual about this distribution and kind of what this question is driving at. Specifically, do the heights appear to be reported or actually measured? Now, if the heights were actually measured and people's heights are kind of random, you would expect the frequency of the last digit of those measurements to be equal. You would expect a uniform distribution, right? You expect about the same number of zeros as you have ones, as you have twos, as you have threes, which is what happens for the sort of odd numbers, 1, 2, 3, and 4, and 6, 7, 8, and 9, right? Those are fairly equally spread out, right? There's the same number of data values in each of those classes. But we have these peaks at we have these peaks at 0 and 5, which would seem to indicate something fishy is going on. So when you ask somebody how tall they are, we normally are not that precise about it. We usually round, right? Now, in the United States, we measure our height in feet and inches. So I would say I'm 5'10", right? That's my height. But that's not precise, right? We don't usually use decimal places, but in most other countries, you're going to measure your height in meters, and you might be tempted to round, right? So it doesn't really say what units are being used here. That might help us get a better idea of the background of what's going on with this data. But if you were asked to estimate your height in meters and you're going to like go to one decimal place, or even 2 decimal places, you're more likely to end on a 0 or a 5 if you're just reporting it yourself, because it's a casual measurement. It's a, it's not a precise way. When I say I'm 5'10", that is not a precise measurement of my height. It's more casual than that. I'm trying to think of a better word for it. It's I can't really seem to think of a better word other than to say it's a casual way of reporting my height. If you were to get more precise about it and measure it to a certain number of decimal places, you might say I'm 5.8372 feet tall. And in that case, my height ends in a 2, right? That's the last digit of my height. But if I'm going to just and if people aren't really interested in that level of precision, and I'm just having a casual conversation, or just from off the top of my head, because I don't remember my height to that many decimal places. Even if I measured it one time, I wouldn't bother to remember it to that many decimal places. I might say I'm 5.85 or 5.80, right? I would end it on a more, rounded value when sharing my height with other people. So because the peaks are at 0 and 5, and maybe I'm belaboring the point here. Maybe I should have just stopped like 5 minutes ago, but it appears the heights are reported. If people are just going to use 0 and 5 as the last digit, it seems like those are values you would expect people to use as the last digit if they were just being imprecise and casual and just kind of giving their approximate height rather than their precise height. If it was precisely measured, you would expect the values to be evenly distributed for the last digit, not with peaks at 0 and 5. So that would be the short way of interpreting or answering that question and interpreting the data. And so these are the kind of things you want to look for when you're dealing with a set of data is, what could explain why the data looks the way it does. And you have to be careful about the way the data is collected. That's another thing that this question is driving at, right? And that's something that we maybe, I guess I'm going to tell you, I'm recording the chapter 2 videos first before I go back and do chapter 1. So kind of, I'm thinking in the future, I'm going to talk about chapter 1, but when you're watching this video, you would have already watched chapter 1 videos. And we talk about that in chapter 1 as well, is, we have to be careful about the way data is collected. How are samples constructed? And are we getting the data for people's heights by having them self-report, or do we actually measure it ourselves? And that makes a difference in what the data looks like. And that's what this question's driving at. All right, so that's the end. I believe that's the end. It looks like I have one more screen here. No, sorry. One more thing. If we collect a large sample of blood platelet counts, and if our sample includes a single outlier. Okay, so I did not define this, and I don't know if it gets defined in chapter 1. I can't remember because I haven't done those videos yet. And I didn't talk about this in 2.1 either. I know that for a fact. And I forgot to put it in my original PowerPoint with the definitions. So when I saw this question on the homework, I just took a picture of it and I thought I would talk about it there. So an outlier is a single data value that is far away. Now, far is kind of a relative term, but is far away from the rest of the data values. And I was thinking about this with our Animal Crossing data. You could make the argument that 70 is an outlier because it's kind of by itself. It's the only one that's low. I said that funny. It's the only one that is that low. The rest of the data values are 80 or higher, and we only have one at 70. So you could make the argument that 70 is an outlier. And in a lot of cases, outliers are ignored because usually there is some explanation for why, that data value did not occur with the rest of the data values. So maybe that was a disgruntled, critical reviewer who did not like the first Animal Crossing, does not like the developer company. Maybe there's some agenda behind why they gave it a 70, and that doesn't really reflect the general review scores for that particular game. And so we can maybe ignore that one. And by ignoring it, you might get a better idea of the population that you're studying, right? And so that's what an outlier is. So you want to be on the lookout for these. Now, if you get more than one outlier, it's not really an outlier anymore. So if we had 2 critical review scores at 70, 70 is not really an outlier anymore. There's obviously a group of people that feel that way about the game, and that's a population that we maybe would be interested in studying or just being aware of. But with just one value, it could be misrecorded, right? Maybe the reviewer meant for it to be a 90, but somebody accidentally read it as a 70, and that's how it got reported. Again, there's a lot of reasons why outliers might occur. So that's what an outlier is, and that's why I have this problem at the end of this video. I wanted to define that term so you'd know what that meant. And how will that outlier appear in a histogram? So this is actually one of your homework problems, and it's going to look the same in your homework because there's not really any way to vary this question. So I'm basically going to do this homework problem for you, and that's your reward for sticking it out to the end of the video, I guess. So let's read our options here. Since a histogram shows frequencies, not individual data values, the outlier will not appear. That is not the case. Every data value gets counted, and so it should be somewhere in the histogram. It needs to be counted somewhere in the histogram. So instead, the outlier increases the frequency for its class by 1. I mean, that is true. Every data value increases the frequency for its class by 1, but the outlier won't be with the other data values. It's far away from the rest of them, so it's not going to be hidden in another class with other data values. If it's in a class with other data values, it's not an outlier. Right, so A is not the correct answer there. B, the outlier will appear as a bar from all the other bars with a height that corresponds to a frequency of 1. That one sounds correct to me. But with these questions on the homework, you have to read each option carefully, because sometimes one will sound correct the first time you read it, but then when you read a later one, you'll say, well, that one actually sounds more correct, and there's a problem with this one that I didn't see originally. There's some information left out that should have been there or something like that. So make sure you read all of your options before you make your selection. The outlier will appear as the tallest bar. That one's just absurd. The outlier is by itself and it's the only one. It's going to be the lowest bar, if anything. And the outlier will appear, so C doesn't sound correct. The outlier will appear as a tall bar. Again, no, that doesn't sound correct, right? So B is the right one for this particular answer. Now, it's B for me. The one way they can vary it is to scramble the order that these sentences are given in. So you want to pick the sentence that says the outlier will appear as a bar far from all the other bars. That might be option C for you on your homework. So they might scramble the order of that, but make sure you choose the sentence that says that. Okay, so again, I took a section that probably should have taken 30 minutes and I talked about it for an hour. So I apologize for the length of the video, but hopefully you feel like you have a pretty good understanding of histograms, and that you're going to be okay on the homework. If you have any questions about this topic and you're one of my students, please contact me, and I'll see you in the next video for section 2.3.